So today we're going to take a look at, can we predict some stock values? We've talked about linear and quadratic rates of change, and today we're going to talk about polynomials. So functions can help us understand how one quantity changes with respect to another. This is especially important when our money is involved. So today we're going to take a look at a value of a stock in a large sportswear combination over 1 month of time. So after T days, this is the value of the stock. Well, is it linear? Well, let's take a look here. Is it linear? Well, how much is this going up by? In 3 days, it goes up by $20.70. And then what happens this next day? Well, it's going down, and it's going down $31.50. Oh my, and then it drops again, drops $62.01. The stock keeps dropping, negative $71.10. So is it linear? No, because that rate of change is different. So is it quadratic? Well, let's see. We talked a little bit about how we can look at those second differences. So this is going down $52.20. This is going down $30.06, and then it goes down $9. So I'm going to say no, it's not. Because that difference isn't the same. The second difference is not the same. So if we take a look at here, here's a grade of F, the graph of that stock. So let's see, estimate the value when the stocks start to decrease. Well, sometimes we think it's right when it's going down, but actually it's going up, and now it's starting to decrease right in here. So I would say between days 2 and 3. Does the stock value ever reach 0? Let's see, does it ever reach 0? And there's no x-intercept. On which day during the 28 period is the value of the stock the highest? Well, it looks like right here it's the highest point. So I would say day 28. And that looks about, what are we counting by? 25. So maybe about $450. Is the rate of change of S increasing or decreasing of the interval 3 to 9? So 3 to 9. Well, look at that. It's decreasing. And why? Well, it's concave down. It's going down. Use the table to calculate the average rate of change from 3 to 6 and 3 to 9. So let's see. 3 is right here. So that looks like about 250. Oh, and we could use the table, right? So we could go back up here and say, oh, we know how much it is on day 3. So we could do 250.7. Wait, what interval are we doing here? 3 to 6. So that should be our, okay. So let's see here. 219.20 minus 250.7 over 6 minus 3. Well, that turns out to be about 1050 a day. And then 9 to 6. Let's use our table here. So 157.10 minus 219.2 over 9 minus 6. And that gives us 20.7. So is that correct? Yes. Well, it's definitely decreasing because it's definitely going down. So the first 20 days of February, use the graph to average the day where the value of the stock changes the fastest. Well, it's looking really here and here, and maybe somewhere on this side as it's going up again, but it's changing really quickly down there. So I would say about day 10. So what we looked at is something called a polynomial here, okay? So a polynomial is a function that's written out in this long form. So a polynomial would be like 5x cubed plus 6x squared minus 2x plus 8. the leading term is that number that's out in front. So that would be, so that leading term is that one out in front, a sub n, in our case is 5. The degree is the highest power. In this case, it's that n. So highest power. And in our case, it is 3. And the leading coefficient is that number out in front. So that would be 5. So if we take a look at all of these here, find the leading coefficient. Well, our leading coefficient, here's our highest power. So it's 3 and it's of degree 4. The leading coefficient here would be, there's our highest power, -7 in degree 3. And this one, what's our leading coefficient? Well, it's 4, and this is like x to the 0, so it's 0. Now, just like when we looked at our stock market graph that has highs and lows, there are some relative extremas. And a local relative extrema is within a certain location. The absolute is also called the global, and that's the highest point. So if we take a look at this one, there's some minimums. There's a minimum here and here. So at x equals -4 and x equals 0. And there's a max. There's 2 high points here. So at x equals -2 and x equals 3. Now where's the absolute? The absolute highest point right here, the absolute maximum is 2 at x equals 3. And the absolute lowest point, well, do you guys see how this keeps going down, down, and down? So there are none. So if we take a look at this next one, is there a relative minimum? Well, it keeps going lower and lower, so there's not a relative minimum. And there is a relative max right here at x equals 1. There's no relative minimum. But our absolute maximum, the absolute highest point, is right here at 3 at x equals 1. So we could take a look at a couple more of these here. So our relative minimum. Well, here's a minimum right here. So there's one at x equals 2. Our relative max, well, there's 2 high points. So at x equals -4 and x equals 3. But the absolute lowest, well, this keeps going down, so there's not one. But the absolute max, the highest point is right here of 2 at x equals 3. So again, relative minimums, where are our low points? Well, there's 2 low points. So x equals -3 and x equals 3. And what about some maximums? Well, this is a high point, and a high point. So there's 3 of these. So at x equals -4, x equals 0, and x equals 5. But our absolute minimum right here is at -3 at x equals -3. And our absolute max is this top one here at a height of 4 at x equals 5. So, a couple things. Fun facts about these polynomials. Between 2 real zeros of a polynomial, there must be at least one local max or local min. And that makes sense. It's just saying if it crosses the x-axis, it's either got to be a local max or a local min. And the other thing, polynomial of even degrees must either have a global max or a global min. So that's just saying if it's even, there's either the highest point or the lowest point. So the last thing we're going to talk about is points of inflection. Points of inflection are when it changes from going concave up to concave down. So like here, we're concave up, and then right about here it changes. So at x equals -1, and now we're concave down, boom, it changes again to concave up. All right, and then this last one here. For each of the following intervals, determine if the rate of change of g is increasing or decreasing. Explain your reasoning. So from 3 to 4. Well, I'm going to say that rate of change is increasing. Well, why is it increasing? Well, we could say that because it's concave up and it's getting steeper. So from -4 to -3. Well, what is this? It's concave down. So it has to be slowing down. So it is decreasing. And again, that seems weird because it's steep, but it's becoming less negative there. It's getting less steep. So -1 to 1, -1 to 1. Well, is that concave up or concave down? It's concave down, so it's decreasing because it's concave down. And then 1 to 2. Well, that is concave up, so it is increasing. And again, that seems a little strange, but it's becoming less negative, so that actually means it's getting bigger. All right, for the next one, for example, for 0 to 3, the number of cars in a parking lot at time t can be modeled by a function here. Based on this model, at what time does the number of cars in the parking lot change from increasing to decreasing? So this is one we would have to graph and estimate from our calculators. All right, and I think we're going to skip this last one. Well, maybe we'll look at this last one. A polynomial function has x-intercepts at 0 and 4. Which of the following statements must be true? It's a quadratic. Well, we don't know about that. It must change concavity from 0 to 4. Absolute maximum at 2. We don't know about that. A relative max or minimum. And we don't know about the concavity. It could be concave down, but it has to have a relative max or min because it has to either be going like that or like this.